This is going to be different from the typical educational videos I make. Normally, I break down one individual HVAC engineering concept and provide a little context. In this video, I'm going to connect the dots by outlining the HVAC design process as a whole. A bunch of concepts will come up: time series, load components, sensible versus latent, peak versus block, psychrometrics, air balancing. But this time, it's all about context, how these things fit into the process. If you want more detail, you have to check out my previous videos. And lastly, I'm going to use HVAKR as a guide through the process. I try and leave HVAKR out of my educational videos, but in this case, it's just the best way to provide helpful visuals of the process as a whole. Let's get into it. The first step is putting together your basis of design. This is where you're going to define your building and your design requirements. Your building location is going to determine your weather and your elevation. Defining your envelope or your building data is where we're going to set U values for our walls, roof, solar heating coefficients for our glazing, but also we need to capture the thermal mass, because when we're doing load calcs, there is a time delay in the heat transfer that makes its way through a building. For example, a high weight concrete wall might have a time series that looks like this, fairly even distribution across time. That means it's going to take longer for the heat to get through the wall, whereas a metal wall will have a much more instantaneous heat transfer going through. Next, we're going to define our space types. Space types and their usage are going to determine the set points that we're trying to achieve in the space, our internal load requirements like number of people, the people load, plug load, etc., and also any independent airflow requirements. Independent airflow requirements like ventilation and exhaust are dictated by the space type, how much outdoor air it needs to receive or how much air needs to be rejected, and they do affect the loads, even exhaust, which we'll get to in a few steps. Once you've defined your basis of design, then you're ready to go to step 2, defining spaces. When defining your spaces, you're going to capture the geometry and the size of your space, as well as the space type, aka the space usage. The geometry and the space type are going to determine things like number of people and your plug load and your lighting load, as well as any ventilation or exhaust requirements. When defining the space usage, we're really determining the internal loads of this space: people, equipment, lighting, and ventilation, which is driven by that ventilation requirement. And you'll notice here, some of these loads are sensible and some of them are latent. People sensible load is going to be the dry heat generated by the occupants, and people latent load is the heat added through moisture. Once we've defined all of our spaces, we're ready for the third step, which is defining the envelope. In defining the envelope, we're going to assign our walls, windows, roof, and slab. And based on these areas and orientations, we're going to get our external load and determine our infiltration. Once we have our wall areas, roof areas, glazing areas defined, we're now able to compute the external load for our spaces. And now you see here, in addition to my internal load and my ventilation load, I've got my external load. And this actually leads us to our next milestone: 4, compute space loads. Now, in HVAKR, the computation itself just happens in real time as I provide these inputs. But let's pause for a second to discuss what space loads actually are. These are the load components that originate from the space. It does not mean that these loads are manifest within the space. So, for example, the ventilation load may originate from the outdoor air requirement for the occupants in the space, but the load itself is often handled at the system level in the central unit. The space never sees it directly. Now, in a few steps, we're going to use a portion of these space loads to calculate our supply CFMs. We're going to use the space sensible load to do that. But when it comes to sizing our system as a whole, we can't just sum up all of our space loads. The reason being, these are space peak loads, the maximum load that each space sees. And we can see here that this particular space sees its peak at about 2-3 p.m. We need to determine our system peak, or our block load. One space may peak in the morning, another space may peak in the afternoon, and to determine our system peak, we need to find our coincident max load, the overall maximum load our system sees when we account for different peak times. This leads us to our next step, zoning. Zoning is the first step in defining our system structure. We're going to group spaces into thermal zones, usually based on like usage and similar exposures, and then we're going to group our zones into systems based on a central piece of equipment. Not only does this define our system structure, but it is also necessary to determine our block load. Milestone number 6 is compute zone and system loads. Again, this happened automatically, But let's look at the difference between our space peaks and our zone or our system peaks. This space here peaks in the morning, midday. This is what the load profile looks for that individual space. But when you take the entire floor as a whole, this entire system, this is the coincident load, and this peaks at 3 p.m. This right here is going to be my block load for the system, and this is what I'm going to be sizing my central equipment based on. So now that we've gone through these steps, we've determined our space peaks, we've determined our zone peaks, and we've determined our overall system peak or block. And from here, we have two questions we need to answer. The first one is how much airflow and at what temperature do I need to supply to each space? The second question is how do I size my equipment to accomplish that? We have the loads, but how do we handle them? This brings us to step 7, system configuration. When we configure a system, this is where we define how the HVAC system is structured, how airflow is moving through the system, where outdoor air is being introduced, where our cooling and heating components are. Ultimately, we're defining where the load is being handled. So let me give you an example. These are my zones served under my central system, and I'm going to configure this like a standard air handler serving VAVs, but in doing so, I'm defining where airflow is coming in and where load is being handled. So at this central unit, I'm bringing in outside air here. My outside air intake is coming in at the system level, and I'm specifying how much. This is going to be driven by my space types and their ventilation requirements, how much ventilation needs to come in, and there's load associated with that. Next, return air is going to be coming back to the system level as well. So this central unit has outside air intake, and then it has return air coming back from the system. I'm going to provide cooling at the central unit. So this is my cooling component. And here I'm going to specify the desired leaving air temperature. So if I want 55-degree air cooling the spaces, this is where I'm going to set that. And I could also specify preheat or heating at this unit. So let's add a preheat coil. And here I'm not going to handle all of the load. I'm just going to preheat it. So let's go with 60 degrees preheat at the central unit. Next, this airflow, which is going to be cooled in the summer and preheated in the winter, is going to be distributed to my zones. So selecting these zones, I can configure these as a VAV with reheat. So what I'm saying here is that air, which is conditioned at the central unit, is now going to be finally heated at the VAVs when we're in heating mode. So hence 90 degrees being supplied to the space. But in setting this up and configuring the system, I'm telling it my outside air is coming in here and it's mixing with my return air before it hits my cooling or heating coils. Then that's being distributed to my zones. My VAVs don't have any additional cooling. They just have reheat. They're just doing additional heating. There are a bunch of different system types you could configure just by specifying where air is coming in, where it's mixing, and where your cooling and heating components are. But just to recap, what I've defined here is that my ventilation air is going to be handled at this central unit, and 100% of my cooling load is going to be handled by this cooling coil. In heating, I've specified that only a portion of my heating load is handled by this coil, and the remainder of it is going to be handled by this coil at the terminal units. So that's me configuring and designing my system. In doing so, incidentally, I've also specified the desired supply air temperatures. I want 55-degree air going to the space to condition it in summer, and then in winter, I'm targeting 90-degree air going into the space to heat it. With these supply air temperatures, we can now calculate our load-determined airflow. Let's get some CFMs. This is step 8, calculate load-determined space CFM. So now that we've calculated where the load is being handled and what the supply air temperature is going to be going into the space, we need to determine how much airflow is going into the space. And to do that, we use the following variables. We need our space-sensible load, which I'll touch on in a second. We need the supply air temperature, which we've set, and the indoor air set point, the indoor air temperature, which we also set as part of our space type. We're going to use these together with the sensible heat equation, this is simplified, to determine the CFM required. HVAKR does this calculation automatically. We can see when I'm looking at an individual space, I can see what the supply airflow is for that space. And it's using this space sensible load. Now, why is it using this space sensible? If you recall, there are a number of load components that originate from this space, but only some of them are actually being handled by conditioned air injected into the space. That includes all of your interior sensible loads, people sensible, equipment and plug loads, lighting loads. It also includes your external sensible loads, like loads from your walls, roof, slab, windows. It does not include latent loads or ventilation. So why don't we include the ventilation and the latent load when calculating airflow for the space? The reason is those load components are being handled at the central unit. That load is not handled directly in the space, and as you can see here, my ventilation load comes in, and that portion is handled in the process of getting the air down to 55 degrees. Likewise, the latent load from the space is being handled at the central unit because that's where the moisture is extracted. In getting the temperature to 55, moisture is not extracted directly inside the space and handling it at the source. It's coming back and it's being handled here. So by the time you have 55-degree air, there's a portion of the load that's already handled. Supplying that air to the space needs to capture the remainder of the load. That's direct to the space. That's your space-sensible load. So that's why the space-sensible is broken out in this report here. And I can quickly run the numbers. So for this space, 8680, 1.08 is a simplification, but I'm going to have 72-degree set point minus my 55-degree supply comes out to 470 CFM. That's what we got there. In the air balancing step in the program, we can see all of those space CFMs listed out really clearly, but there is one more critical step before we can lock in our sizing. That's step 9, air balancing. Heating and cooling loads are not the only factor in setting proper CFMs. You'll also want to check other requirements like pressurization, differentials. In healthcare and labs, you have a lot of ancillary requirements about how spaces need to be pressurized, either positively or negatively, and that's going to change what your design CFMs are for your spaces. The other thing you want to check is the system balance, and this can manifest in many ways, but let me just give you one example. Let's say in these restrooms and shower rooms, I need to exhaust 300 and 100, a total of 400 CFM, and I've made the design decision not to supply air directly. I'm going to transfer air. So the shower room has 100 CFM of exhaust, but I'm not going to supply that. I'm going to transfer that from an adjacent space. So here, I'm going to be transferring in 100 CFM to the shower room. It's going to be pulling that air out of this adjacent corridor. So here, I'm transferring out 100 CFM. Now, I'm losing 100 CFM in this corridor. So instead of returning the full amount, I'm going to be returning 100 CFM less. That is 100 CFM less return air going back to my system, which is going to affect the psychrometrics, the air mixing. It's ultimately going to affect my coil sizing. Let's look at one more air balancing consideration, this time on the system level. If I'm looking at my overall totals for my system, I have 1700 CFM of outside air coming into the system. This correlates directly to this setup, 1700 CFM of outside air intake, mixing with the return that I've now set. There is currently 400 CFM of exhaust in this system, but let's pretend we had 2000 CFM of exhaust present under my system. That means this 1700 CFM of outside air is not making up for that additional exhaust. In some scenarios, you may need to artificially increase the amount of outside air intake to balance your system as a whole, to make up for the amount of air that's being rejected from your system. And in doing so, this also affects your psychrometrics, your air mixing, and your coil sizing. Now, instead of 1700 CFM coming in and mixing with my return air, I now have 2000. This is going to increase my coil size due to more outside air being introduced. I can demonstrate this concept on the psych chart. So let's say originally, theoretically, you have 1500 CFM of outdoor air, that's state 1, that's coming into my system. Then state 2, I have 7000 CFM of return air, that's mixing to get a mixed air state right here. And then I'm targeting 55 degrees leaving. That returns a total load of about 220,000 BTUs. Now, in the process of air balancing, let's say I had to increase the amount of outside air coming in, and I also removed some return air coming back. My mixed air state is now slightly more extreme, and my total load jumped from 220 to 245,000 BTUs. This process of balancing the system fine-tunes our coil load. Our actual coil load is different from our theoretical loads because of system design and airflow considerations. All right, once you've finished balancing your airflows and your sizing is locked in, we can now move on to step 10, and I'm grouping a lot of things together here, but you select your equipment, layout system, size duct. Now, we're putting our design down on paper. I won't go too deep here, but generally, my workflow at this stage is to start with my diffuser layout, and I'm going to pick up the amount of CFM required per diffuser. HVAKR does this automatically because we have the space CFMs already set. Otherwise, you would just set those CFMs yourself based on the calculations you did in step 8 and 9. Once my diffusers are placed, I like to set my equipment, terminal unit here. We'll say my central unit is out here. And then with my air outlets and inlets placed, my equipment placed in their approximate locations, I'm going to connect the dots, run my ductwork. That was my medium pressure, and here is my low pressure. From here, if you're doing this by hand, you would sum up the CFM in each section of duct. You would use the sizing parameters for that type of duct, pressure drop and velocity, to determine your duct size, and you would do your external static pressure calcs to determine your fan power required. In HVAKR, I can just hit the size button and it'll run that automatically. I will get my duct sizes, and I will even get my critical path and my external static for that path. This is just a portion of the drawing. Obviously, you would go and do this for your entire system. And beyond this, steps 11 and beyond are going to be fleshing this out. So you'll be adding details, building out your equipment schedules, finalizing your selections, adding your specifications, doing coordination with other trades, and keeping up with all of the revisions that are happening until you get through your design stage. My focus here on steps 1 through 10 were more so on the HVAC engineering steps. I hope this video provides more context on all of my other videos where I go into more detail about these concepts. But there we have it. I hope that was helpful.